Warm welcome to yet another discussion on GATE Electronics and Communication Network Theory related papers. So today we are checking GATE 2016 Set 2. There are 7 questions for network theory for that examination. So moving to the first question, in the circuit shown below, Vs is a constant voltage source and IL is a constant current load. The value of IL that maximizes the power absorbed by the constant current load is. So it is from maximum power transfer theorem. IL is actually a constant current load. So IL is actually the constant current flowing through a particular load, right? So from maximum power transfer theorem, we know that for maximum power transfer, the load resistance must be the complex conjugate of source resistance. That means here it is given as source voltage as Vs and similarly source resistance as R, right? Then for maximum power transfer, the load resistance must be R itself, right? So the current flowing in the circuit is IL, that is marked as the current. IL is the current flowing through this load resistor, right? So IL equal to Vs by R plus R, 2R, right? So the answer is IL equal to Vs by 2R. Moving to the next question, the switch has been in position 1 for a long time and abruptly changes to position 2 at t equal to 0, right? If time t is in seconds, the capacitor voltage Vc in volts for t greater than 0 is given by, right? So for t less than 0, switch is in position 1 and steady state is attained. So we have to calculate the initial voltage first, right? Initial voltage. So for that I am drawing the initial steady state circuit plus minus 10 volt 3 ohm. As steady state attained, the capacitor becomes open circuit. So the initial voltage equal to 10 into 2 ohm resistance divided by total resistance 2 plus 3, 5. So answer is 4 volt. 4 volt is the initial voltage. Now I have to draw at t equal to 0, switch is moved to position 2. So for final steady state, the circuit becomes this way around, right? It is 4 ohm. So again, for calculating the final steady state, the capacitor becomes open circuit and the 4 ohm, one arm of the 4 ohm is open circuit or it is not connected. So actually the 4 ohm has no effect in this circuit. So final voltage V final equal to current 5 ampere into this resistance, that is 2 ohm. So 5 into 2 equal to 10 volt, right? Now we can write the capacitor charging discharging expression, that is Vc of t. Capacitor charging discharging expression is Vc of t equal to V final minus V initial e raised to minus at. Now we can substitute the values to this expression. Vc of t equal to V final is 10 minus again 10 minus initial voltage. Initial voltage is 4 e raised to minus at. For calculating A is actually 1 by time constant. Here for t greater than 0, the circuit is basically a RC circuit. So 1 by time constant is RC. Now R equal to 6 ohm. Because for calculating the value of resistance, we have to deactivate the source. That means we have to kill the current source. Then the circuit consists of only this 4 ohm and this 2 ohm. So 4 ohm and 2 ohm is in series. So total resistance is 4 plus 2 is 6. 6 into capacitance. Capacitance is 0.1. That is 1 by 0.6. 1 by 0.6 equal to 1.66. So we can substitute all these terms. 10 minus 4 is 6 e raised to minus. The answer is in terms of 0.6. So e raised to minus t by 0.6. So the answer is 10 minus 6 e raised to minus t by 0.6. So now we can check the next question. Again, this is also a direct question. The figure shows an RLC circuit with a sinusoidal current source. At resonance, the ratio IL by IR, that is the ratio of the magnitudes of the inductor current phasor and the resistor current phasor. So it is basically a parallel RLC circuit with R, L and C. All those values are 10 and the applied signal is Im sin omega mt. We know that at resonance, IL or IC, right? IL or IC becomes Q times, Q is the quality factor, Q times the resistor current, right? Q times the resistor current. So here we have to calculate IL by IR and it is given as magnitude part, right? So IL by IR we have to evaluate it equal to Q. But for a parallel RLC circuit, Q is given by R into root of C by L. So we can substitute the values. R equal to 10 ohm, C and L, C equal to 10 microfarad, right? L equal to 10 millihenry, equal to 10 into 10 cancel. So 10 raised to, this is 10 raised to minus 6, right? Okay. So that is 10 raised to minus 3. I am using the 10 ohm inside the square bracket. That turns out to be 100 into 10 raised to minus 3. So that is root of 0.1. Root of 0.1 equal to 0.316. So the answer is 0.316. Another thing to notice, this is the ratio of capacitor current to resistor current also, right? During resonance, inductor current is IL equal to Q times I angle minus 90 degree, where I is the applied current. Similarly, I capacitor equal to Q times I angle plus 90 degree, right? Moving to the next question, the Z parameter matrix for the two-port network is shown as 2j omega, j omega, j omega, 3 plus 2j omega, where the entries are in ohm. Suppose ZB j omega, right? ZB j omega equal to RB plus j omega. Then the value of RB in ohm equal to, right? So we have to check the relationship between Z matrix and a T network. Here we have to calculate ZB, right? ZC is actually this term, that is j omega, that is a sharing term, and Z11, this term 2 j omega equal to ZA plus ZC. Similarly, on the output side, 3 plus 2 j omega, right? 3 plus 2 j omega, that is Z22. Z22 is the impedance of all the elements in the second loop, right? So Z22 equal to ZB plus ZC. But ZC is j omega. So 3 plus 2 j omega equal to ZB plus j omega, or ZB equal to 3 plus j omega, right? And in the question it is marked as ZB j omega equal to RB plus j omega, and we have to calculate RB in ohm, right? So RB turns out to be 3. Now moving to a 2-mark question. In the given circuit, each resistor has a value equal to 1 ohm. What is the equivalent resistance across the terminals A and B, right? Each resistor has a value equal to 1 ohm and we have to calculate the total resistance value between the points A and B, right? For that, we have to recollect a star delta basic conversion. This is the basic conversion rule. For a delta connected resistor of value 3 ohm is converted to a star network by dividing 3, right? So here the delta connected resistor has all values as 3 ohm, and for a star connected network the value turns out to be 1 ohm. So applying first delta to star conversion, that is I am applying delta to star conversion at this point, right? So I can mark, actually the resistance, all resistance value are 1 ohm. So I can mark this resistance value as 1 by 3, right? 1 by 3. So this is the circuit. I am connecting the delta connected resistor to a star connected resistor. So the circuit turns out to be in this way, and the value is 1 by 3. Here also 1 by 3, again another 1 by 3. So, and we have to calculate the resistance value between these 2 points too. Now I am replacing the inner star, this is a star network, right, to a delta connected value, right. So I am repeating, I am now replacing the inner star to a delta connector. Inner star has a resistor value of 1 plus 1 by 3 or 4 by 3 ohm, right. So now I have to connect the star connected 4 by 3 ohm inside this circuit, and converting the star connected 4 by 3 ohm to a delta connected network, that is 4 by 3 ohm to a delta connected network, turns out to be just 4. Why? Because I have multiplied by 3 ohm. So it turns out to be 4 by 3 into 3. So I am connecting that delta connected network here, right? Delta connected network here, again here, and again here, right? The value of this resistance is 4 by 3 into 3, that is 4 ohm. Again this also 4 ohm, again this also 4 ohm. We have to calculate the resistance between these 2 points also. Now the circuit can be redrawn as 1 ohm, here it is 1 ohm, right, 1 ohm parallel with 4 ohm, right, 1 ohm parallel with 4 ohm, and again at this point another 1 ohm parallel with 4 ohm. Now again 1 ohm parallel with 4 ohm, and it is connected in this way, 1 ohm 4 ohm, 1 ohm 4 ohm. So that means the total impedance is 1 parallel 4, this combination, right, in parallel with, right, in parallel with 1 parallel 4 plus 1 parallel 4. Now we can check what is this 1 parallel 4. 1 parallel 4 is 1 into 4, 4 by 1 plus 4 is 5. So 4 by 5, that is this term is 4 by 5 parallel with 1 parallel 4, 4 by 5 plus again another 4 by 5, that is 8 by 5. This is the final answer, and we can calculate this term also. 4 by 5 parallel 8 by 5, that is 4 by 5 into 8 by 5 divided by 4 plus 8, 12 by 5. So answer is 32 by 5 into 1 by 12, right. So that is 8 by 15 ohm, right. Cancelling 4 from both numerator and denominator, 8 by, right, 8 by 5 into 3, right. So 8 by 15, 8 by 15 ohm is the final answer. Now moving to the next question, the switch S in the circuit shown has been closed for a long time. It is opened at time t equal to 0 and remains open that. Assume that the diode has 0 reverse current and 0 forward voltage drop. The steady state magnitude of the capacitor voltage Vc in volts is. So initially the switch is closed, right. So before t less than 0, the switch is closed and the inductor attains steady state, that is inductor behaves as a short circuit. So we can first calculate the initial current flowing through this inductor. So for t less than 0, the circuit turns out to be in this way, plus minus 10 volt, 1 ohm. Next switch is closed and the inductor is short circuited, right. Now the current is initial current I initial equal to 10 by 1, that is 10 ampere. So I am marking this initial current here also, I initial equal to 10 ampere. Now for t greater than 0, it is mentioned as diode is almost an ideal one, 0 reverse current and 0 forward voltage drop. So it is ideal one. So for t greater than 0, we can draw the circuit. And again for t greater than 0, the inductor attains steady state. That is, it finally reaches a short circuit condition. So I am finally plotting for t greater than 0, right. This is diode. So in this circuit, diode is actually an ideal one. So I can replace this diode with an short circuit too. So I am replacing it as short circuit. Now there is an initial current of 10 ampere. So I have to either mark it as a parallel combination of 10 ampere by S, right? 10 ampere by S, or series combination of 10 ampere into the inductor value, right? So that turns out to be 10 millivolt. So anyway, I am marking it as a parallel combination of current source. So 10 ampere by S, 10 by S. Again, be careful about the direction of the current here, right? The inductor charging current is in this direction. Similarly, its discharging current must also be in this direction. That's why I marked it as downward, right? But if it is capacitor, it is just in opposite direction. So now I am writing the node equation at this point, and actually the node voltage is Vc itself. So writing the node equation, 10 by S, right? The leaving current 10 by S plus the node voltage Vc by the impedance. I am marking it as SL because I will later apply the value of inductor and capacitor to avoid complexity. So plus Vc by SL plus Vc divided by 1 by Sc, right? Or Sc Vc equal to 0. Or minus 10 by S equal to Vc by, I can take actually Vc outside, right? So minus 10 by S equal to Vc into Sc plus 1 by Sl. Now Vc equal to minus 10 by S divided by Sc plus 1 by Sl. Now multiplying both the numerator and denominator by Sl, that is minus 10 by S into Sl, that is minus 10L, right? Minus 10L divided by S square Lc plus 1. But we know the Laplace transform of sine omega t equal to omega by S square plus omega square. So we have to convert it into this form. That is Vc, now Vc equal to minus 10L, and I am taking Lc outside the term. So minus 10L divided by Lc into 1 by S square plus 1 by Lc, right? Now I have to make the numerator term as omega, or omega is actually 1 by root Lc here. So I have to multiply numerator by 1 by root Lc and denominator by 1 by root Lc. So that is Vc equal to minus 10L by Lc and multiplying denominator by 1 by root Lc or root Lc into, here the numerator side it is 1 by root Lc into S square plus 1 by Lc, right? Now we can check what is this term. So that is minus 10L by Lc. So LL cancelled. So minus 10 by C into root of Lc equal to minus 10 into 1 root C cancelled. So root of L by C, that is equal to minus 10 into L is 1 millihenry. So 10 raised to minus 3 divided by capacitance 10 into 10 raised to minus 6, all in root. That is minus 10 into root of 10 raised to minus 3, 10 raised to minus 6 cancel. Denominator side 10 raised to minus 3. Going to numerator side 10 raised to 3, 10 raised to 3 by 10. That is 100. So answer is minus 100. Here the coefficient is minus 100. So Vc equal to minus 100 into 1 by root Lc, right? Vc equal to minus 100 into 1 by root Lc divided by S square plus 1 by Lc. Now we can convert it into time domain, right? So Vc of t equal to minus 100 into sine of omega t. Omega is actually here 1 by root Lc. So 1 by root Lc t. So coming back to the question, the steady state magnitude of the capacitor voltage Vc in volts is. So we have calculated the capacitor voltage with keeping here plus and negative. So the answer turns out to be capacitor voltage equal to, here it is given as negative plus. So answer Vc of t equal to 100 sine 1 by root Lc t, right? So the steady state magnitude part is 100. So the answer is 100. Now moving to the last question in this video tutorial. In the circuit shown in the figure, we have to calculate the magnitude of the current through R2. Magnitude of the current through R2. So first of all we have to write the node equation. I am marking this node, right, the dependent source node as V, right, V. So I am writing the node equation at that point, that is V minus 60 V minus 60 by 5 plus V minus Vx, this is Vx, V minus Vx by 3 equal to 0.04 Vx. As 0.0 Vx, the current source is entering the node. Now I am substituting V in terms of Vx. From the figure, Vx equal to the voltage V into this branch resistance, that is 5 ohm divided by total resistance, right? 5 plus 3. As 5 ohm and 3 ohm are serially connected, the voltage will split into Vx and balance as voltage across R2. So Vx equal to 5V by 8 or V equal to 8Vx by 5. Now substituting this term for V, that is 8Vx by 5 into 5 is 25 minus 60 by 5. 60 by 5 is 12 plus again for V, that is 8Vx by 15 minus Vx by 3 equal to 0.04 Vx. From that, Vx can be taken as common, that is 8 by 25 plus 8 by 15, right? Next term is minus 1 by 3. Next term is minus 0.04 equal to 12. This term also. So now Vx equal to 12 divided by all these terms. This term rounds up to 0.48. So Vx equal to 25. As Vx equal to 25, we have to calculate the magnitude of the current through this R2, right? Vx is the voltage across R3. The same current must flow through R2 and R3. That is IR2 equal to the voltage 25 divided by resistance. Resistance is 5 equal to 5 ampere. So the answer is 5 ampere, and this current must flow through R2 and R3 as it is serially connected. So for more gate tutorials, subscribe my channel. So now I am signing out till we meet again with another gate tutorial. Thank you.